I'm going to talk a little bit about databases and containers and where to put your data and your containers and how to containerize databases and what some of your choices are. I'm going to tell you a little bit about Aerospike. That's sort of the sponsored portion of the talk. I promise to keep it quick. And then I'll talk a little bit about how to actually do the kind of database and container tricks, scaling out both an application layer and a database layer with Aerospike. So I'm going to start with the conclusions. I always think that's the best thing to do in one of these talks. And what we know about containers and containerization is it makes the development process faster and easier. Your developers are bundling in their tools and their libraries. They're doing it in their environment. They're building up Docker files and Docker images so that you can very rapidly push things into production without having to go through a big hassle about which libraries and which containers, right? That's the big win about containers. The problem with the stateless design methodology is not everything is stateless. Most things, in fact, are not stateless. So where do you put your data? That's what we're going to talk about today. So happy developers because you got your containers, I've got fast development, but then I have to use databases. Ephemeral containers, which is the pattern where you use ephemeral storage and it comes and goes, developers can get along very well with that. They'll often create patterns where they'll just restore a base image into their container and then be off and running, do their unit tests, be happy. When you actually take that to production, you've got a lot of problems. So where to put the data is hard. And I will note that, just as a sidelight, all of our testing does show that for an in-memory database like Aerospike, containers have almost no virtualization tax. So, as you all know, containers really are a stand-in in many ways for the old virtual machine technology. Has its pluses and minuses, minus being security, but the plus of performance we've definitely seen in production environments. So those are the conclusions. Now we'll just have a long and drawn-out discussion about the details. So what we have had before containers is a fairly broken model of deployment. So the existing models, which is to say the old models before containerization, was you do your work on your version control system, right? You do all that work, and your developer would be interacting with the files. They would go into a QA environment, and that QA environment would have particular things like your chef system, your automation system, and then something would push into production run by sysadmins, and usually things will break in subtle ways. And that's one of the things containers fixes. So containers are good for encapsulation, deployment, isolation. Those are all the stateless portions. So the state, some of the state is contained, as I was saying, in the kinds of libraries that you have. But the real state, the state of the application itself, is going to be contained in the database. So let's go and pause for a second and talk about what is meant by the stateless architecture, because I get confused sometimes because, stateless? what do you really mean? Of course, there's tons of state in every application. You got to have state. So I went and looked it up, and what a stateless architecture really means is that the application tier does not require stickiness at the load balancer level. Any application server can take any request. That's really what people mean by a stateless architecture. There's nothing special about anything. Now the problem occurs even in a stateless model because if your database is too slow, you'll typically put a cache in, right? That's what everyone does. If you're going to put a cache in, you probably are going to end up putting that cache inside the container and inside the application layer. That's common practice. However, if you do that, you'll find that stickiness is kind of necessary. So that in-database cache paradigm tends to break, even though it is technically correct that any application container can take any request. You're relying for the stability of your service on the idea that you're going to have enough cache stickiness to get decent hit rates. Essentially a bad pattern. So what a bunch of the stateless guys talk about is you're going to have state outside of each individual container, but it's going to have to be a really fast database that is easily accessible from each individual container. One that essentially doesn't require those kinds of caching paradigms. Now, of course, you can put a cache layer that is independent and not in container, that's out of container. But I'm going to suggest at some point, why not just have, instead of a separate cache layer, just have a faster database? This is where clustered, in-memory, NoSQL are all the keywords you're going to want to look for building at-scale web services. Now, you're often going to need some portions of your application interacting with true transactional systems or legacy systems. But I suggest that, and as I've read through and talked to people who deploy in these environments, that fast database layer is kind of a key to making stateless systems work. Okay, so stateless architecture says no state in the app tier. But you need to have state, so where are you going to put it? Well, the first answer is don't containerize your data. Have an outside web service. And in the talk after talk that I go to, that's what most people say. But then there's this desire, hey, wait a minute, I just built up this architecture around containers. I launch and I scale, and my scale is all driven through my container-based tools. So I want to containerize my things, because that's what my devs are doing, and that's what my deployment guys are doing. How can I possibly do this? So if you're not going to containerize your data, how are you going to do it? Well, the most obvious way is to use a cloud service. And if you're already invested in and have tied yourself to a particular cloud service, that can seem pretty attractive. But there's the obvious problem. You have now just tied yourself to an individual cloud service. Your benefit of going to containers was to abstract yourself from those cloud services. So your developers can be running in a dev environment on their laptop, possibly disconnected, certainly not at the whims of an internet connection to their cloud service. So I'm going to suggest if you're going to take that cloud service route, why did you bother containerizing, since you've already jammed yourself into a cloud service? Now, there is a way to avoid that, which is to take the microservice approach and have different microservices. And when a particular microservice is running in the cloud, it does one thing. When it's running on a local environment, it's running somewhere else. To me, that seems like it's on the complicated side. So to me, the cloud services architecture is not a great way to go about this. If you're going to go the cloud service route for your data, you might as well just get everything, go all in on that cloud service. Just go with your AMIs, go and use Elastic Beanstalk for your messaging. There's no point in trying to go Kafka, which can be multi-cloud and is at a higher level, if you're going to go and go containers in general. But if you're going to containers, I suggest that's not the great way to go. Now, the other thing you can do is you can use a two-track system where in deployment you're doing one thing and in dev you're doing something else. And we already had that slide, right? We already said that's kind of broken. The whole point of containers was to have the same style of system, even the same exact technology and management system, working for your dev and working for your ops cycle. So I'm going to step for a second. A lot of people use this meme, containerize all the things, clean all the things. And what's that meme from? This is why I will never be an adult. So containerizing all your things is pretty much an insult to the idea. You really shouldn't containerize all the things, because then you just end up containerizing everything and your life ends up kind of miserable. So don't containerize all the things. But let's say you really do believe in containerization. I've just given you the argument against containerizing your data. Okay, that's all well and good. But there's some really, if you really believe in this system and you do want to run multi-environment, you don't want to get involved with, don't want to tie yourself to a single database API, how can you do it? I have found two core patterns around containerizing, working with data and state in a containerized system. Now, the first one says, I'm going to use ephemeral storage that is tied to an individual container, and then use what I call, in my mind, a shadow device, And I'll go through this in a little more detail. But the cloud, the Docker manager and also Kubernetes calls this persistent volumes. And that pattern essentially says you've got an abstract network storage device of a higher level of persistence. And then you have a close ephemeral system. So when you restart the container, it all goes away, but you stored it somewhere on the network. But the network's too slow. Remember, we want a fast database in order to make the whole system work in general. And again, I'll go through this in a little more detail. The second thing to do is to have persistent storage within the container system itself. Now, the problem there is that limits where that container launches, so you end up with more complexity, and your container system isn't as abstract as perhaps you wanted it to be. On the other hand, you are using a container system. You'll have some slightly different launch patterns for your devs and for your ops guys, but as you'll see, they're only a little bit different. It's not quite so bad. So these are the two patterns that I think are practical here. So in the ephemeral system, sorry for the rather ugly diagram here, but basically what you do is you have these block devices or storage devices which are in container, which is to say they're on the same physical machine, thus they're fast enough. And you can also think about this even if you're using an in-memory RAM database, right? These are all kinds of storage, whether it be fast flash, which is very similar to RAM in performance in some cases. I won't go into that in this talk. But essentially all of this stuff goes away. So in cases where you've got either RAM or you've got local SSD, but it's ephemeral. So in cases where it's ephemeral, what you need is you need the database to be writing to not just this persistent device locally, but also writing to this persistent volume. Now the benefit here is you're only writing in large streaming blocks, so speed isn't as much of an issue. Write performance will be an issue, there will be some latency involved, but at least you're in this nice abstract environment. So what happens is you don't read from the persistent device, except on startup. On startup, or possibly on warm-up, depending on how your database supports this configuration, you will be doing those reads. Now with Aerospike, when we have this, and by the way, if you're using Amazon, the only thing that persists in the Amazon architecture is, well, S2, S3, but the most persistent thing is EBS. So this is exactly the kind of pattern you're going to use using containers or even virtual machines within the Amazon environment. You need a database that supports this kind of remote but highly persistent abstract network device like EBS, right? So just think EBS here, as well as having a ephemeral but much, much, much faster read-write device that is in system. So think about this as your i2 or i3 instance, which can be, what the new i3s are, the big ones are, it's like 6 tera or something like that, right? So think about trying to build a 6 tera EBS volume or sliced volume with 1 million transactions per second. That gets to be really, really expensive in EBS. But it's actually kind of practical if you are only doing the writes to that system. It's still big, but at least you're not paying for provisioned IOPS, right? And you're not having to deal with the read latency, which gets pretty messy on EBS. So this is the kind of pattern you use, and the good news is it's supported by Docker. So Docker, through its persistent volume plugins, you'll see plugins for iSCSI devices. If you're using a bare metal implementation where you want to have this persistent layer, it's across the network, it's iSCSI. But usually there's a huge ton of it, right? You've got some enterprise volume manager in the background. Ceph is a great system for this. There's now more appliances out there that I'm finding that support the open source Ceph distributed volume and object system. They're all essentially sort of EBS-like. But Docker has a plugin system, and so does Kubernetes, I believe, has also this very same persistent volume system. Okay, the other way to do it is you actually have persistent local attach. In persistent local attach, you're essentially saying, I can only launch this cluster, launch this database container in this particular place. And you're going to have to create some scripts to do that. Now, Docker gives you some help on this, so it's not quite as grungy as all that. But you end up being able to say, this particular cluster, this particular storage device is here, it's on this virtual machine, and you've sort of broken that containers can be anywhere motto. You might have to, in fact, only have individual containers launching on a particular machine or relaunching on a particular machine in order to make your cluster. So you actually have to have a system that supports this. So as an example, Google Compute Engine does not have an EBS-style store. Simply doesn't have it. They do have an S3-style store. That's Google Cloud Storage, but they don't allow you to write it, map it as a block store. So they don't have EBS. So, but that's okay. Google just does it differently. What they do have is they have what they call persistent disks, and some of those are persistent SSDs, and they are far, far, far cheaper and at a reasonable latency compared to EBS. So if someone came to me and said, I want to run a database in GCE, and it's got to be a fast read-write database, an operational database, I'm going to say you really want to look in Google at persistent SSDs. Once you do that, you don't end up with having that shadow device, because you just have a different storage option. So instead, you launch your container. Should I do my, so I'm going to tell you how Docker helps with all this. Okay, so you're going to launch your container, and that container is going to need the locally attached storage. Now, Docker gives you just a little bit of help here, which you can use to make this a little less grungy, which they call the containerized data pattern. In the containerized data pattern, you create a container that literally just has this piece of storage in it. It has really nothing else. You can use almost any image. It doesn't have your software. It doesn't have your database on it, right? And so your ops guy or your local launch scripts, when you're running a dev environment, just creates a bunch of these containers and gives them a set of well-known names. So those are those containers. Now, separately, you create your database containers, and you use this very particular flag when you're doing your Docker run, which is volumes from. So with volumes from, and then you specify basically this individual container. So you're still using a lot of hard-coded addresses, but you've got a lot more of the Docker tooling available for you in order to be able to list these objects, set their names, inspect them, all this kind of stuff. And then what ends up happening is, what Docker intends here, is the ability to be able to do things like flip and manage your versions, get your libraries right, all the great things about Docker within this container without having to deal with the problem of where's the storage. So this two-container pattern is one of the things Docker really intends you to do when dealing with this kind of storage. So this is what you do when you've got this kind of local system. Those are the two patterns. I'm going to pause here for a minute. Any questions about this idea of either using what I call the shadow disk system with slow, independent network attach versus local attach? Any questions about it? Okay. So now I'm going to tell you a little bit about Aerospike. Sorry, I'm going to keep it brief. So what is Aerospike? Aerospike is a database that I and the company created that is really a large distributed hash table. That's what we thought. We thought, you know what? People are building a lot of great analytics systems. In 2008, 2009, there's a lot of work to create Greenplum and Aster and Vertica as a column store, great database. Hadoop was already happening. Spark hadn't quite happened yet. And we said, well, what about the problem of the edge database? We looked at things like the Dynamo paper, not DynamoDB, but we also thought about the bigtable pattern. The bigtable pattern says, in bigtable, make each row independent, figure out how to make it independent, and rely on the fact that storage is now cheaper so you can play the old database trick of using more denormalized patterns as opposed to a fully normal form and relying on relational semantics for correctness. And turns out none of this is really, it was somewhat novel at the time, but it was all part of the way NoSQL, what we now call NoSQL. Of course, it has to have clustering. It has to have rebalancing. But that's really what we looked at. How do you build a large distributed hash table that is truly order 1 to get any key within the system? And then let's build some cool stuff around it. Let's build replication in. Let's build load balancing. Let's build in autoscale, horizontal autoscale. And let's make it really fast. So instead of sticking with the single-threaded patterns that were common in some of the other databases, or using a higher level language like Java, we stuck with working on multi-core, multi-threaded systems because multi-core, it's only getting more and more multi-core as years go by. And we also really predicated the system on Flash. So our clustering is baked in, and our core Flash algorithms are also very much what we do. And we made it open source. So we ran the company as a closed source company for about 3 years. We now have the open source version available. We run the company in the same model as Mongo, where you have the company in charge of the code base, so not Apache model. And then we have some features in the system that are what we call overbox or extra. A couple points about the internal architecture. So one of the big differentiators, one of the choices we made when designing the system was to say, one of the things that slows down a database is trying to persist the index. And that's kind of a deep concept because any index, as we all know as programmers, it's got a lot of little bits of things that have to point to other things. And when you do an insert or an update, you have to update all those things. And if they're persistent, this is hard to get right and do in a reliable fashion. And I would argue even Oracle still doesn't get it right 20 years later. I had a friend of mine whose production Oracle system crashed, and it was unrecoverable. It got its indexes wrong, and you run the Oracle recovery tool, and it gives up. So they lost all their data. They had to go to backups, right? So this happens from time to time. It's a hard problem, a really hard problem. So we punted on the hard problem, being lazy people, and we said, you know what? What you actually care about is persisting your data, not your index. Makes the problem a lot easier. Means that you can do updates by doing a copy on write, which is always good, right? As a database, you want to not be updating in place, because what if you get a partial update? You always have to update anyway. So those were some of our core ideas that make both reads very fast, because the other point about this is since the primary index is in RAM, it's very, very parallel, because it's fast, and RAM access is pretty parallel too. Very multi-core. It turns out in order to be able to drive Flash efficiently, you want to have what's called high queue depth, because it's a high bandwidth device, but it's a device where there's a lot of chips working in parallel. It's sort of like if you were building an old 3-par system and you had a huge number of spindles. Each device is kind of like that. So, excuse me. Oh, a new version of Docker. How pleasant. I guess I hadn't connected to the network enough today. But I also don't know. Let's see, I've still got slide control. Great. When I looked at Flash and how Flash works, Flash is actually very good for databases if you ignore the file system and use the old Oracle trick of running in direct access mode. Now, Linus is against that in Linux. He actually took ODirect flag out of the kernel. And he basically said the only people who should be using this are database guys. There's a whole bunch of other people who are trying to use storage devices in raw mode and direct mode. They don't know what they're doing. So he removed it from the header, and he basically said anyone who's building a database can just define it themselves. We'll keep supporting it in the kernel, we just won't expose it. So it's an old database trick to run in direct mode, go around the file system, and build your own data layouts. And what this means in production is we get kind of insanely good predictable performance. Now these are some old numbers. We're now well past a lot of these. The other idea is in distributed. What we figured out that you should do is you should really rely on the randomness of your hash if you're going to build a great DHT. And that ended up also being a very deep idea within the system. So, we're all taught in computer science that you can't rely on a collision-resistant hash function. If you've got a hash function, you are reducing the amount of data, you will get collisions. Well, that's kind of interesting because we now have some much more sophisticated hash functions with no detected collisions. When you're talking about a 160-bit hash function, you're talking about collisions that exist. Maybe if you have the number of atoms in the universe all tagged, you have a reasonable chance at a collision. I mean, they're really good hash functions out there. And so the one that we selected, RIPE-MD160, which was developed in Europe by the RIPE Authority, it's used in Bitcoin. It's been assaulted. There's no collisions yet. And if you're building a DHT, and we check, by the way, we store the key. So if you were ever to get a collision, we would in fact detect it. But we've never detected one either. That creates a lot of interesting possibilities when you're building a DHT to say, we don't have to deal with chaining. We're just going to say, well, if we're going to assume that there's never a collision because it hasn't been found yet. And we use that consistent hash function to be able to split up into partitions. We can then move those partitions around, and we can build our own consensus algorithm. One of the great things about how this works is when a node drops, the load is randomly distributed onto the rest of the cluster. So as opposed to building a sharding system with a primary and a secondary, where if the primary drops, the secondary takes all the load, what we do is randomly distribute the remainder of the load. Turns out that has a lot of benefits when you're actually in production. So there's a lot of people who are out there using this system. It's not a new system by any stretch of the imagination. What you'll notice is a lot of folks in AdTech have really taken to it. That's where Aerospike is very well known. However, we're now being used in a lot of telecom cases and a few very interesting financial services cases. I'm going to walk through a couple of those real quick, then we'll get back to containers. It turns out Aerospike is really interesting for machine learning. There are two use cases, and this Nielsen Marketing Cloud I stole these guys' slides. They're friends of mine. I gave a talk down there in Israel yesterday. It turns out that the best kind of machine learning these days is online machine learning. In online machine learning, you don't build a second batch system, build your models, and then propagate forward your models. You build one stream. That one stream of data has your events coming in. It has this preparation step, feature selection, runs things through the model, and actually gives you results. In this case, these guys are using it for audience classification. What they found was they needed two things to run their system. First of all, they needed a good store of user data. And that's about the size and shape of the cluster that they're using there. What's much more interesting about the case is they needed a model store. And I hadn't really appreciated the problem of model storage until I talked to these guys. It turns out a bunch of other Aerospike users are doing it. If you're doing online machine learning, and those models are changing on a regular basis. These guys update their models, I believe, every 5 to 10 seconds in 100 event microbatches. And they have a lot of models. They have about 50,000 models running concurrently in order to do audience classification. So this is at some pretty serious scale. They're dealing with millions of events per second and hundreds of billions per day. It turns out being able to store those models is critical because model performance, as relearning occurs, can sometimes drop. In those cases, you need to be able to roll back non-performing models quickly and efficiently. Models, in another customer case I found, models can sometimes start adapting to data problems that occur upstage in the pipeline. So imagine for a moment that you've got some kind of a partial outage and bad data flowing in as according to this system. The cool thing about online machine learning is your models back here will actually figure that out and start adapting to poor data. which is great. This is why we don't need data scientists, right? The problem is what happens when that data problem is fixed. Now the models are underperforming because they've learned how to deal with bad data. And this has happened in production. I've run into a bunch of cases and talked to the guys about it. So it turns out in this case you really need a persistent model store because you'll almost certainly want to be able to roll back to old model versions. So any of you who are dabbling in online learning, this is pretty interesting. If you're using TensorFlow, for example, TensorFlow has essentially the same kind of system where everything's online, and they use a model store, which is actually, of course it's Google, of their own design, and it's a peer-to-peer shared system also using 100-element microbatches. So this core design, if you're rolling your own, of needing this model store, pretty interesting stuff. Okay, another interesting case for a high-scale key-value store. This I ran into in one of our financial services customers. It turns out to do proper risk analysis, you don't just want each user's or account's current trade status. You want what's called the in-flight trades, the trades that have yet to settle. The greatest amount of risk occurs, in fact, in unsettled trades, not in settled trades, even for derivatives. The old style of building an order management system, you use streaming methodologies, and what's called the fixed positions, the trade status occurs in a pipeline. It's not stored in a centralized database. They do this because the trade flow is too high for a traditional relational system. However, that's the fun part. It's really when you have unsettled obligations and bid match failures is when risk is way, way, way up and your bank may be failing, i.e. 2008. So what these guys did was they said for tighter risk analysis, we want all unsettled trades, including parent and child relationships, because modern trades get split. And we want a centralized database. But we need a 1 million transaction per second database to track all of the state changes in a centralized place, as opposed to using a stateless in-flight system. Another interesting case is fraud, and that I would call a modest-sized systems. These are often in sort of the 1 to 5 terabyte range. Flash is still important because it has to be correct intraday. You do need a system of record that is legally binding, essentially, and doing that with the traditional systems in a write-only mode. And that's the key to this architecture. It's almost like what I was saying with EBS. If you're going slow, it's kind of okay to just use the to have a relational system like that. Fraud prevention, another really interesting case. I like fraud. If your business has fraud, that means your business has money. And where there's money, there's fraud. So it's usually good if you have fraud. The interesting thing is what's called the move from beyond the rules engine. So in old transaction processing systems, they would use batch processes even month by month to figure out what fraud rules should be in place, anti-fraud rules, and then they'd load them into essentially a SQL-oriented system and run them on their in-flight transactions. However, people now they've got a lot more data at their disposal. It's finer grained data. They can use techniques like machine learning that are not easily codified in SQL. My guys who are doing this are running at really high levels of scale, much higher than my AdTech guys. Some interesting cases in Telco are coming up. In Telco, you need to now be able to do traffic shaping on a per flow basis based on user preference. What that means is, you remember how we used to pay for our cell phone bills by the minute? Well, the minute, I mean, really? Minutes? So you only had one database write and one check for status every minute while you were on a phone call. Now what every telco has to do is do billing by the packet, which creates a much greater load. Second of all is what's called routing personalization. Imagine the case where you've got, you want to press that button that says, I get free streaming from Netflix. A lot of telcos have implemented that now. It came out on my carrier this week. In that case, you want to provide traffic shaping. Traffic shaping means you need a little bit of state. You need to be able to look at recent flows. So the router, now every router in the cell phone network has to do a database lookup to figure out if you have traffic shaping turned on, what the recent flow numbers are, et cetera, et cetera. So now we've turned our telco problem, instead of a moment-by-moment, minute-by-minute routing and billing, into a packet-by-packet decision engine, which is pretty cool. In terms of our AdTech guys, we've seen a move to putting more and more data on the edge. So systems that used to be about 1 to 5 terabytes in terms of keeping all the recent cookies and all recent behavior are starting to push up into the 10 to 40 terabyte range, simply because they want to track more information per user, and they've found business value in doing that. And of course, just running a high-scale website, having a persistent cache is a pretty cool thing. Okay, product part over, let's go back to containers. So the entire point of containers was to reduce complexity and to keep a particular abstraction all through these 3 stages in the pipeline. We get encapsulation of dependencies, and the biggest thing that I always see is in the modern age, when I'm dealing with, just imagine a node application. With a node application, you may be dealing with thousands of libraries and dependencies, and you have figured out exactly which set of dependencies works at a given time, and you can put all of that then, and one particular set of libraries, all into one container spec. And sometimes that requires, well, rolling back a version of this and forward a version of that. It happens to me, certainly. So you've got a specific environment. Now, with containers, you can separate all of that out and even run that in multiple machines with, let's say, multiple versions of Python. You've got some apps that are 3, some versions that are 2, all of that stuff. What's an example of that? Those of you who haven't used, imagine this compared to a virtual machine. In the old days, which is to say about 3 years ago, I would have created a virtual machine, set up my libraries correctly, and said, clone the virtual machine. This is how long a Docker file spec is that essentially allows you to do the same thing, which is pretty fly. I will just take a moment to pick out what I detest about Docker, which is this common pattern of doing things like apt-get update. Once I see a pattern like this, I realize that it's not ready for production, because what I run on my laptop and what I run next week in production, who knows what it is, right? I did an apt-get update. Unless you have really locked down where apt-get update comes from and where your entire service chain comes from and all those libraries as part of apt-get, you don't really know. So that's my particular bone to pick about trying to take Docker into production. But Docker gives you the tools, right? You don't have to do this. It's just that most of the Docker files and images I see do this. Let's take a moment to go over the picture of Docker for those of you who aren't familiar. This took me a little bit of time in the early days. So great, we've got essentially these images, and we have essentially a fleet of these Docker engines. A Docker engine is a piece of real hardware, a particular chassis, it's got a bunch of CPUs, and it's going to carry each one of the virtual machines. Compose is what takes one of those Docker files, and there's other ways to do it, but it basically compiles that Docker file into an image with all the blocks that you need so that you can then run it in the Docker engine. And the cool thing that we'll talk about a little bit more is using Swarm. Swarm is Docker's system for being able to abstract and scale out within the cluster. Okay, so what we do want as part of our container system is the ability to do horizontal scaling and the ability to have the kind of high availability and redundancy that we all desire in development systems. So when you're using a clustered database, do you get these things? Data redundancy, yes. All the NoSQL guys have forms of clustering and redundance. When you have dynamic self-discovery, that means you don't require a load balancer in the middle, and most NoSQL databases do that as well, right? So you want to be able to have a library in the middle that allows you to find data in different places. You want to be able to handle either automatic or sometimes manual. There's arguments for both. Cases of being able to take containers out or have them fail. And you want to be able to have that application tier deal with, I have a network, a piece of abstract database infrastructure, like I talked about. This is where you're going to store your state, even though it can be a little complex to set it up. So let's talk about it again. There's a different set of pictures. There's this question about whether you're going to go internal or external. Internal is where you have the case of having that local storage. External is when you use this shadow write concept. Within the data container, that's the other case that I was talking about, where you're using local storage and you're using that containerized pattern that Docker supports. Okay, so when you're doing clustering, you've got a couple of choices. One of the things you can use is you can have each one of your cluster entities support a different DNS entry. You can use single DNS entries for each element in the cluster, or you can have a separate IP address for each. So I'm going to run you through a little bit of this, how to actually do it. But what I will tell you is this has not yet been, I usually do this as a live demo, but I haven't updated it through the more recent versions of Docker, which is, of course, many people's complaint about Docker is it keeps updating in a non-backwards compatible fashion. So if you want to actually see the demo, first of all, you can go to our GitHub repository. It has all the code that I'm going to sort of sketch out for you right now. It also has a video of the guy running it. I'm still working on getting it updated to the current Docker. Okay, so first of all, you want that environment where you can just build an app. The app in this case is a very simple Python Flask app, so it's using Flask as its case. What you'll see in the code is a voting app. It brings up a website, allows you 3 choices of things to vote for. When you scale this out, it's a pretty simple system with Docker. The system is that Docker provides essentially the HA proxy layer, and it allows you to simply be able to add web server containers. And the HA proxy, since the web server entities are registered with it, provides all of the routing internally. And I'm not going through exactly how to do that in terms of the lines of code. Again, it's in the code repository. It's a pretty simple system. Requirements.txt is, of course, the interesting part, which is in the repo. Now, the Docker Compose also uses the Aerospike instance. That's what we're going to go through in a minute. The counter itself is a domain that we created just to be able to do the demo. Okay, so when you are running, taking your single web app and then rolling this out, all of it is talking to the same database cluster underlying. It's sort of the easy part of this pattern. Now, what I like about this pattern and what I've seen succeed customer after customer is one way to think about this is you're separating out the CPU scale component from the storage scale component. You're not pushing storage into the compute or vice versa. There's a lot of efficiencies that occur within, say, data grids when you push data and compute close together, but there's a lot of benefits by abstracting this out. What I recommend when you think through architecturally is what I'm starting to call the one-hop architecture. You should be able to run different web services and microservices where you are only doing exactly one hop out to your data. And if you do that, you probably have a highly performant application. If you have to do a hop to your database and then a hop to your storage engine and a hop to your cache in the middle, you're dealing with a lot of complexity in terms of extra components, management complexity, and also consistency violations that occur when there's cache. So Docker networking, because we're talking about multi-network environments, what ends up happening within this is, now these are the Docker daemons. Again, this is from the demo case. Each one of these daemons is running within its own system, and it's using an overlay network. So what happens when you create each one of these within their swarm is containers get created in different places. So you've got HA proxy, which creates endpoints, and those are all running within the network and the bridge overlay network. Now, in the first case, you end up with just one web app, but then you can scale them out very easily. Oh, I think that slide got lost. I apologize. So the case within this is basically this is the kind of command you're going to be able to see to actually be able to create the container swarms. So in this case, what we're doing is we're using TLS certification to be able to register an individual app with the Swarm host. It's also important in these to be able to register the actual application with the upper level. So I apologize for the hand-wavy nature of this portion of the program, but once you actually go through that process of being able to scale out the application server itself, again, look to the demo code, it's pretty straightforward, it's only a few files. You have the second problem of wanting to independently scale out the data layer. Now, when you do that, the goal is you're not using the HA system that is contained in Docker, because Aerospike, like all of the other NoSQL systems, includes that layer within the client itself. So essentially, it's baked in here. You'll see the same kind of pattern within Cassandra. So what these guys need to do is they usually need to be able to find one element of the cluster that they're running against, which usually means they only need one DNS entry. So what you'll see in the example code is the ability to be able to register and use by having these guys go into the Swarm console and register one DNS entry within console. And as long as one of these is alive, everything will be able to sort itself out. That's a very common NoSQL pattern. One of the benefits of using all of this stuff is Docker's Event API. That's how we actually, within the demo environment, we're able to get the fact that a server is launching to change the DNS entries within the Swarm console environment. So you'll see some references to that. That's where you're essentially, the Aerospike Interlock plugin is doing the add remove node. So when nodes are added and removed, it's updating config files, etc. So that's a pretty key piece of technology. And that's really all it has to do. It just has to look occasionally for events and update. So in summary, Docker and container can be beneficial. I find it to be technology that's not without its thorns. But as you're seeing here, there are patterns that you can use to be able to productize your database. You are going to need to store your state somewhere, and then in a stateless design, that's going to be your database. And there are patterns that exist. First of all, containerizing your data within those data container objects, or using outboard storage. But you can build all of this, and so you'll have a container environment for your app developers that's local, that uses a 1 or 2 node cluster locally, and still has the same kinds of patterns so that those containers will run in ops environments. It's all possible and doable. So thanks very much. Thanks for, again, coming up into the sponsored track. Hopefully the sponsored portion wasn't terribly onerous. The code's out there in terms of our Docker demo. Our Docker images are all registered under the Aerospike area, and there's deployment guides for Docker up on our website. We are an open source project, so if you want to just get started, that's where I'm going to send you. So thanks very much.